So I've been affiliated with George Mason so long, I'm one of the few things that Henry Butler doesn't take credit for. Or actually, maybe he does take credit for. I don't know. As Don said, I do empirical work as an economist, but I teach in the law school. That's just an interesting, just to give you some sort of context here. Presumably when y'all went to law school, you didn't have classes on statistics and things like that. Law schools have sort of changed, particularly at sort of the higher end of the rankings. I regularly teach classes in scientific evidence, statistics for lawyers, things like that, and virtually all my research is on empirical work. When I talk to students, I tell them, if you look at kind of legal scholarship from days gone by, it was mostly some old guy just making stuff up, right? And then you ended up getting us sort of younger guys in there to sort of say, well, how do you know that? And at best, the empirical evidence would be some version of, well, in my 18 months in practice, I saw this case 3 times, right? Not anything that you would count as sort of real evidence. So one of the things that we've sort of been doing in legal scholarship and legal education has been sort of pushing this idea that there are ways to sort of test ideas that we have. There are ways that we can sort of make more certain that the things that we're teaching actually sort of accord with the real world. Obviously we don't get everything right, but we are sort of making a big push in that direction. So what I'm teaching you today is something that we sort of integrate in the classroom for law students today. So hopefully, a number of years from now in your courtrooms, you will see sort of lawyers who are better engaged with this stuff, who do less lying with numbers. That's our goal. So if we're going to put this in the context of scientific evidence, our big concepts that we're interested in, you all know from Daubert, are reliability and relevance, right? Those are sort of the 2 Daubert prongs. They have nice intersections with sort of the way we think about statistics even outside of the courtroom. We use a little bit different language. So when you hear the term reliability, often in science or in statistics, we talk about internal validity. That's a term you might remember from your own sort of high school science days, right? This idea of internal validity. Is the statistical test, is the statistical experiment sort of correct? Is it accurate? Is it well done? Is it sort of applied correctly? Those sorts of things. But just as much as we care about that, we care about whether or not the evidence is also relevant. So you in the courtroom are seeing some research that presumably wasn't done with the sole purpose of presenting evidence in your courtroom. It was done for some other purpose, ideally. And that other purpose may not be completely well aligned with the facts in the case in front of you. And so you all, under the federal system, are sort of tasked with this idea of how far is too far, right? How much can we take sort of research or statistical work that was done in some other context and essentially extrapolate it to the context that we see in front of us, the facts that we see in front of us in the case. In scientific speak, this is known as external validity. That is, if I believe my experiment, if I believe my statistical test, I think it's right for the setting that I tested it in, but usually I'm interested in settings beyond that. Will this experiment replicate when someone else does it in their laboratory? Will this regression, we'll talk about regressions later, will this regression hold up if we apply it to different data? Right? This question of how much can you generalize or how much can you extrapolate is a core idea in science, and it has this nice analog under Daubert in this relevance kind of inquiry. Okay? So we're going to try to integrate all this language together so we're all sort of speaking the same language. But let's start out with sort of the basics, Statistics 101. In some versions of this class, we call this statistics in an hour, but they gave me an hour and 10 minutes, so I can't do that. I can't do that now. But that's still what we're trying to do. We're trying to sort of give you some basic, some basics of statistics and sort of see how they fit into these relevance and reliability sort of categories. So when we talk about statistics, we often differentiate between sort of 2 branches or 2 topics. One is descriptive statistics, that is, can we describe the data? and the other one is inferential statistics. And in this first hour, we'll sort of talk about both. But let's start with descriptive statistics. Another term that's sometimes used is summary statistics, and maybe that's even more informative. When we talk about descriptive or summary statistics, we're trying to essentially summarize the data, right? The expert in front of you, or the researcher in his lab or her lab, or the CDC researcher collects a bunch of data, right? And when they communicate about that data, they can't tell you everything about the data. I mean, I suppose they could, right? The statistical agencies have done a better job lately of just sort of dumping their data on the internet. So in principle, you could look at all the data, but you don't have the time. You might not have the ability, might not have the inclination, but you want to know a little bit, right? These COVID dashboards you see on the CDC website or on the New York Times, they're not giving you all the data. They're attempting to sort of summarize the data in a way that might well be useful to you, right? Now here's the trick in terms of lying or not lying with statistics. When we summarize, we want to summarize enough that it makes it useful for you, that it makes it sort of amenable to your time and inclination and your ability. But we don't want to summarize so much that we've misled, right? I'll give you a good example to this, one that's, maybe will hit close to home. So a couple of years ago, a bunch of law schools got sued. It was sort of in the end of the early 2000s, 2008, 2009. A bunch of law schools got sued on essentially fraud claims. And the claims were different sort of case to case, but basically they boiled down to, hey, when I applied to law school and when I agreed to go to your law school, you told me essentially that the average law school graduate makes $90,000 a year. You told me that. That was in your publications. It was in your information. So I did my cost-benefit analysis. I figured it out, and I said, okay, with $90,000 a year, this makes sense for me to go to law school. It's 2008. My friends, none of us are getting jobs, or we're certainly not getting jobs that are paying $90,000 a year. So we're going to bring some fraud suits. Now, virtually all of these fraud suits got thrown out. I don't think any of them got past summary judgment stage. But they got thrown out because it turned out this $90,000 a year number was accurate. If you took the number of law school graduates in the country, you added up what their pay was, you divided by the number of law school graduates, you got something like $90,000. But just because it was accurate doesn't necessarily mean that it was informative. What do I mean by that? Well, if you Google starting law school salaries, and then you click on the image button on Google Images, you get sort of a famous picture. That famous picture, it kind of looks like a mountain range. There's a big hump here, there's a big hump there, right? In the middle of the two humps is about $90,000. But essentially, if you look at the picture really closely, what you'll see is essentially nobody makes $90,000. It's the average, it is the mean, it is accurate, but nobody makes it. Why does nobody make it? Well, because when you come out of law school nowadays, you end up in one of the two humps. One of the humps, we'll call it the New York City hump, right? Has what? An average of about $160,000, $170,000. But the other hump has an average of about $50,000. And what no one told these graduates, or these graduates didn't know, or the applicants didn't know to ask is, hey, do I get to pick which hump I'm in? Right? How do I do that? I like that hump. Well, call me again when you're working the 90 hours and living in Manhattan. But nobody sort of pointed this out to them, right? Yes, $90,000 was the average pay, but you either end up in New York, and how do you end up in New York? Well, there's sort of two options. You go to a really fancy law school and you end up in the top half of your class, or you go to a less fancy law school and you kind of end up number one in your class, and you can have that bigger hump. Right? Otherwise, you end up in this sort of smaller hump. You put those humps together, and you've got a $90,000 average. It was accurate. In a sense, it was reliable, but it wasn't so relevant. It wasn't so informative for these law school applicants, aspiring law school applicants, right? What perhaps would have been more relevant is if the law schools had sort of explained this. Well, what's the problem with explaining this? Well, that little story that I told you, I skipped over lots of details, but if we're really going to be serious about it, this might take a half an hour to explain, right? The picture's nice, the picture's maybe a quick way to explain, but there's a lot of information in there. So you've got this tension, you've got this trade-off. I want to summarize to make sure I can communicate the information sort of quickly in sort of an accessible way, but I worry about summarizing so much that I've obscured the relevant information for people, right? That's going to be the main question in our minds, particularly as a consumer. When you have summarized these data for me, have you summarized them so much that I'm missing kind of what is the interesting point or the important point or the insightful point for the question at hand, okay? All right, so let's sort of start at the beginning. When we've got descriptive statistics, some of the descriptive statistics you already know, you're already familiar with. A mean, an average, right? Everybody knows what that is since at least the 4th grade. It's a very powerful piece of information, right? It's good to know what on average is an outcome. It's good to know, hey, I want to know what is the average positivity rate for COVID at some particular point. That's a useful thing to know. But it's not the only way to summarize that kind of data, right? And it may not be the most appropriate way to summarize that kind of data. There's another bit of descriptive statistics known as a median. So a median you probably also are familiar with, right? Take all the data, line it up from smallest to biggest, pick the one in the middle. Both the mean and the median are giving you some representative sense of the data. It's summarizing the data and telling you something, saying, hey, in general, if I had to guess what an outcome would be, the mean or the median might both be good sort of routes to that guess. Sometimes they're the same, but often they're not, okay? So I'll give you another story. Paul Krugman, you're all sort of aware of. Krugman is a very good trade economist, although he hasn't done much economics in the last 20 years. He's been more of a public intellectual. But one of the things Krugman has been super interested in over the years is sort of what you might think of as inequality, right? He's been writing about it for a long time. It's funny, it's not his actual economic area. His actual economic area is trade. But in his public intellectual stuff, he's interested in inequality. And Krugman, for a long time, has been pushing roughly the following. He sort of says, look, in the last 60, 70 years, the policies of our country in the United States have been bad for the regular guy on the street. And to support this, he sort of says, if you look at median income, right, and you compare the median income of somebody in 1950 to the median income today, and you adjust for price differences and things like that, the median income in 1950 actually exceeds the median income today. And so Krugman says, see, look, what I've been saying is right. The policies that we've had, the direction the country's gone in, have not been good for the regular guy on the street. But if you have a guy like Bruce Johnson in the back, he comes and he says, hey, Krugman, what you're missing is that mean income has gone up a ton, right? Mean income today is lots higher than mean income in 1950, even accounting for price differentials. And Bruce would be right. But guess what? Krugman was right for his statement too. Which is the right statistic to summarize for this question? Well, you've probably talked to enough economists by now to know our answer is almost always, it depends, right? That's what economists always say. It depends. It depends on your view of the question. It depends on your view of what it is you're trying to answer, right? So Bruce Johnson would say, look, Krugman, you're nuts. If I was a regular guy on the street in 1950, fine, maybe I could get a factory job, but that was about it. If I'm a regular guy on the street today, I could be a hedge fund manager, right? And I can make my 2 and 20 and have that be $40 million a year and so on and so forth. And Krugman will say, that's nuts, right? The mean is pulled up by those hedge fund managers with their really high wages, but that's not relevant for the regular guy on the street. And Bruce would come back and he would say, why isn't it relevant, right? You don't have to be born into aristocracy to be a hedge fund manager. Hell, you don't even need a license to be a hedge fund manager, right? What do you have to do to be a hedge fund manager? Talk rich people into giving you their money. That's all you got to do, right? A third guy might come in and say, well, you're sort of both right and you're sort of both wrong. I'm not as optimistic as Bruce to think that anyone can become a hedge fund manager, but I'm also not on board with Paul Krugman because I don't think the median is the right question or is the right thing to look at. What I'm interested in is what is the possible income after taxes and subsidies. So if we do have people like the hedge fund managers, or we do have people like, Dak Prescott just signed a $140 million contract with the Cowboys, right? If we do have people like that, they've expanded the pie. We can now tax a bigger pie and redistribute that pie. And so the average is what's important because the average income is what gives us a sense of how big the pie is. Krugman would, he's kind of an angry guy. He would shake his head and storm off. Right? He would grumble something along the lines of, yeah, but that never happens, right? That never happens. So who's right in this? Should we use mean? Should we use median? It depends on your beliefs about the world. It depends on what particular question you're trying to answer, right? It depends on what you think is relevant for these sorts of questions. From your perspective as a judge, when you've got sort of experts in front of you or lawyers using this kind of information, at a minimum, it's probably useful if someone says, hey, the mean is this and that means this. Say, yeah, but what does the median mean? Or if, vice versa, that somebody else sort of points to the median, ask them, hey, well, what does the mean say? And ask them to explain. Why is the one better than the other, right? Maybe they have a story, and maybe that story sort of accords with your understanding of the situation. But asking the question is probably an important thing to do. Okay? All right. Haven't gotten any questions yet, so we'll sort of go on. Okay. So mean and medians are going to be sort of your first go-to. It's almost everybody's first go-to descriptive statistic. But we've got other descriptive statistics. Oftentimes, sort of a graph of statistics might be the way to sort of best describe and provide lots of information without sort of obscuring too much. So if we go back to my how much do law school graduates make, right? If you had seen the graph, you would have been able to see this story of two big markets, and that makes a big difference. And that would have communicated the information fairly quickly without a lot of effort, right? So sometimes our best descriptive statistics are sort of graphical representations of the data, right? And that can be useful. So if you sort of have experts and they start talking something that seems like gobbledygook to you, ask the question, hey, can you show me that visually? Sometimes the visual representation can sort of provide a lot of description and sort of depth, okay? So that can be useful. All right, let's move on from sort of descriptive statistics on to descriptive statistics of not just a particular piece of information, but descriptive statistics relating to different concepts, right? So we can also have descriptive statistics that sort of talk about how do two variables move together, right? How do two variables move together? Or do they move together? Okay? Many of our policy questions of interest, many of our legal evidentiary questions of interest aren't just about, hey, what is income? Or aren't just about, hey, what is the COVID rate? Sometimes they are. But often what we're interested in is, how do two things move together? Okay? What happens to cancer rates as exposure to some particular product increases, right? Or from a policy perspective, what happens to incomes as education increases? This is a slightly more complicated question than just asking, hey, what's the average cancer rate? Or what's the median income, right? Now we're sort of asking, hey, we've got two sort of phenomenon, and we want to ask, are they related? right? Do they move together? How do they move together? And sort of our primary descriptive statistic for how things move together is known as a correlation coefficient. A correlation coefficient, okay? And what a correlation coefficient does is it merely sort of asks for a representation of, hey, we've got two variables, X and Y. We've got education and income. When education goes up relative to the average, right? So the average education is, let's say, 10 years. This person has, less than that. The person has 8 years of education. This person has more than that. This person has 16 years of it. When someone has relatively more or less education, do we see any associated movement with their income, right? So for this guy who has relatively little education, is his income relatively high relative to the average or relatively low? Or this woman has relatively high education, is her income relatively high or relatively low? What a correlation coefficient does is it sort of asks that question on average. If we take everybody in our data, we look where they are in education relative to the average education, and we find the corresponding amount that they are relative to the average income, and we take the average across that. That's a correlation coefficient. So it's just asking, do these things tend to, on average, move together, or do they move opposite on average? Okay? And the correlation coefficient is bounded between 1 and -1, right? So if it's a positive number, if it's anywhere from 0 to 1, these things on average tend to move together. If it's a negative number, anything from 0 to -1, on average these things sort of move apart or move oppositely, okay? So in the COVID situation, if we have some data on people wearing masks and we've got data on COVID infections, right? The people or the areas that have relatively high masking rates, do they have relatively high or low COVID rates, right? We could use a correlation coefficient to answer that question. Now, it's still just a descriptive question. We're still just describing or summarizing the relationships, right? But it's a reasonable way to summarize these things. Do these tend to move together, okay? Now, there may be all sorts of other differences as between places. Places that have high masking rates might also have relatively high education rates. They might have relatively low obesity rates. They might have all sorts of other stuff that we think might matter. But at least with a correlation coefficient, we're not asking that level of nuance, right? We're not saying, well, what about other differences? All we're doing is we're saying, for these two variables, do they tend to move together or do they tend to move opposite, right? So of course, if somebody presents you with a correlation coefficient, it may be interesting, but you may have lots more questions that you want to ask, right? Oh, is that correlation, is it because of the masks, or is it because of something else that happens to be related to masks? Is that correlation between education and income, is it because of some causal effect of education, or is it because of other stuff that tends to be related to education? We're not asking any of those questions with a correlation coefficient. A correlation is just, hey, on average, descriptively, do these things move together or do they move opposite, okay? So it may be a reasonable first step. It's very rarely the last step in sort of policy questions or legal questions. There's a lot more that we want to do, okay? Okay. Moving on in sort of level of complexity, closely related to a correlation coefficient is something that many of you probably have seen in your courtrooms, known as a regression, okay? A regression, one way to understand a regression is like a fancied up correlation coefficient, or a correlation coefficient where we add some nuance into things, okay? So what a regression coefficient is doing, or a regression model is doing, is it's also trying to ask this question, on average, are things moving together or are they moving opposite? But it's adding in a lot more structure. It's adding in sort of more detail. It's adding in sort of more nuance. what kind of nuance can it be adding in? Well, so as a starting point, right, what a regression is doing is essentially fitting a line to the data, right? So if you imagine in your mind, there's a bunch of data. I see this in sort of an XY space, if you kind of remember helping your kids with their grade school math or something like that. I see a bunch of dots, and I want to put a line through it. What does that line mean? Well, it's doing much what a correlation coefficient was doing. It's sort of telling you, hey, on average, when X goes up, does Y go up? On average, when X goes up, does Y go down? Or is there no relationship at all, right? That's what a regression is doing. It's doing the same thing conceptually that a correlation coefficient is doing, but it's adding some more structure to it. Does that mean it's better? Well, it depends, right? It's more complicated, right? It's sort of harder to do. It's harder to explain. So on the summarizing sort of side of descriptive statistics, there's a cost, right? You move to the more complicated thing. You go from just a number, a correlation coefficient, to a whole model. You've gotten sort of a more complicated thing. It's harder to communicate. It's harder to understand. What do you gain from this cost? You gain, like I said, a bit more detail, a bit more nuance, a bit more structure, okay? The extra structure and nuance that is usually sort of most interesting or most important is one thing that the correlation coefficient can't do that the regression can is account for other stuff going on, right? So if we go and we look at sort of the COVID deaths, and we're trying to sort of relate that to mask policies or something like that, you might say, well, this is interesting. Seems like there's a lot of COVID deaths in these places that do have mask policies or don't, or et cetera. But then immediately you say, hey, but wait a second, maybe the demographics are different in these places. Maybe some places that have certain kinds of mask policies were more likely to have a lot of old people, right? And old people sort of have a higher death rate from COVID. So I would like to know, hey, what happens if you sort of adjust for, or sometimes the language people use, what happens if you control for those different demographics? You can't do that in a correlation, but you can do it in a regression, right? So with a regression, one way to understand a regression is a regression analysis is taking sort of simultaneously all sorts of different correlations into account. I don't just want to look at mask policies and COVID death rates. I want to look at mask policies, COVID death rates, and how old the population is. Or I want to look at death rates, mask policy, how old the population is, and education level of the population. Or I want to look at also, is it a warm climate versus a cold climate? Because the warm climate people are going to be outside more, and so it's sort of less problematic. You would like to adjust for all those things. That's what a regression analysis sort of allows you to do. It's saying, look, while we are simultaneously sort of accounting for all of these other differences, and now I want to go back to the question of mask policies, I no longer have to say to myself, well, what if it's the case that the mask policy places were just different than the other places? When the regression, at least in principle, you've been able to account for those other differences. You've been able, I use the term adjust for those other differences, but often your experts might say, I controlled for those other differences. Right? That's kind of the language people are using in this kind of setting. Okay? It is still just description. It is still just sort of summarizing, but it's summarizing sort of more stuff, or summarizing stuff in a slightly more complicated or nuanced way. Okay? Okay. Again, though, your question should always be, I want to do a trade-off between sort of the simpler model is maybe better because we can communicate it to the jury more, or the expert can communicate it to me more, or we want to sort of be able to keep account of what's going on without sort of huge amounts of complexity. But on the other hand, I don't want to summarize so much that I've missed sort of important nuances or important complications, right? That's sort of the trade-off in this descriptive, this is descriptive kind of project that we want to do, okay? There are two questions Even with the regression, even with sort of a very complicated regression that has adjusted for all sorts of things, there are two questions that still come up. One is a reliability or internal validity question, which is, have you adjusted for enough, right? Is there still something out there that you still need to adjust for and you haven't? Because usually in policy or law, we want to go further than simply saying, hey, descriptively, these things tend to move together. We want to make actual causal statements. Now, causality is going to be the big topic of my second session after the break, but that's where we're aiming for, right? It's not enough if you're sitting in a court in Texas and Vioxx is on trial, Merck's on trial. It's not enough to sort of say, hey, Mr. Garza's experts are saying, look, it looks as though people who take Vioxx are more likely to have heart attacks. Well, okay, that's important, that's interesting, but the tort question is it the case that Vioxx caused the heart attacks, right? Immediately you might say, well, geez, people who take COX-2 inhibitors, they're likely to be older, they're likely to be sort of in worse health. The whole reason they're taking COX-2 inhibitors is because they have arthritis. That means they're maybe not exercising as much, maybe they're higher weight, things like that. Expert, did you adjust for all these things, right? Well, I adjusted for X, Y, and Z, yes, but did you adjust for A, B, and C? The question of how much have you adjusted for? Have you adjusted for enough so that we can feel confident that the relationship is causal, right? Can we feel confident that we have sort of a reliable estimate of not just the correlation, but the causation, right? So like I said, in the second session, we're going to spend a lot of time on how you get from here to there. But for now, that's one of our sort of first questions, right? Is the model adjusting for enough so that we can get there? And that would be a reliability or an internal validity kind of question, a reliability question under Daubert, okay? Second question that you're always going to ask is, well, okay, you did a study. Does that study apply to the situation in front of me, right? This so-called relevance or external validity or generalizability kind of aspect to things. You studied a certain group, you now want to use that as evidence for the case in front of me. Is the group that was studied sort of close enough to the case in front of me? Okay, so let's go back to sort of the Vioxx case. The Garza one was one of the Texas cases that came out at the trial level with a big award for the plaintiffs and later got knocked down on appeal. One of the things that sort of hung up the plaintiffs in Garza was Mr. Garza was much older than the people who had been studied under many of the Vioxx studies. The Vioxx studies in general had samples of people between the ages of 50 and 70. Mr. Garza was like 70, 78 or something like that. Does that matter, right? Does that matter? Is the fact that, even if we believe the original studies, is it the case that because we think there was a relationship between Vioxx and heart attack incidents in this relatively younger population, do we believe we can extrapolate that to the relatively older population, or to Mr. Garza more specifically, right? That question, unfortunately in some sense, is often not going to be a question of mere science, right? Science might be able, or statistics might be able to give us some clues, but in some ways the court, in saying, hey, look, this is up to you, trial judge, figuring out how close is close enough. A lot of us, we sort of dump on the court's holdings in Daubert and Joyner and things like that and say, give the judges more guidance. Unfortunately, at some point, there might not be very strong scientific guidance that's available, right? Is the fact that we saw this heart attack relationship among younger people, is that informative for some older person? Maybe, maybe not. Right? but this question of generalizability is going to be sort of a statistics adjacent question. It's certainly something that you're going to need to sort of work through and think about, and statistics can maybe give you some indications, some hints, like I said, but you're never going to get sort of the, here's when it does and here's when it doesn't kind of answer. But in our last half hour of this session, we're going to talk a bit about some of the hints, some of the things that sort of allow us to feel better about sort of generalizing from one set of studies or one set of regressions or one set of data to a different set of studies, a different set of data, okay? And this, largely speaking, involves this question of inferential statistics. So when I said at the beginning, we kind of break statistics, or at least basic statistics, down into descriptive and inferential. Now what we're going to talk about is inferential statistics. So as the name sort of connotes, inferential statistics is about what can we infer from some data, okay? More specifically, usually when we study things, we don't study things to learn about just the people represented in the data that we're studying. Presumably, yeah, we'd like to learn about them, but we're actually more interested in what can they tell us about a phenomenon more generally, right? That is, when can we learn from a sample, the sample is the data that we're studying, when can we learn from the sample something about the world more generally, or in statistics speak, when can we go from the sample to the population? Is the sample informative for the population? That's sort of the subject of inferential statistics, okay? And it turns out, under certain circumstances, we can feel fairly confident that a sample will teach us about a population. That is, we can go from the thing that we studied to the thing that we want to know about. Turns out there's something known as the law of large numbers. In math, a law is something that is always true if the assumptions are true. What the law of large numbers says is, under certain assumptions, the mean of a sample will necessarily equal the mean of a population. Okay? So what are those assumptions? There are two assumptions in the law of large numbers. So essentially two assumptions that allow us to go from a sample to a population. Those two assumptions are the following. One is there random sampling? Is there random sampling? Random sampling means every single element, every single person of a population has an equal likelihood of showing up in my sample. Okay? If that's true, assumption number one for law of large numbers is satisfied. Second assumption is I have a large enough sample. It's the law of large numbers, it's not the law of small numbers, right? I need a large enough sample. But if I have a random sample that is large enough, law of large numbers, which we've known of since the 1700s, quite frankly, law of large numbers tells us what is true about the mean of the sample will necessarily be true about the mean of the population, okay? The devil, though, of course, is in the details. When do we have random sampling? That should be sort of a threshold question that you're asking yourself. Is the sample that the people are analyzing, that the expert is analyzing, is it really random? Is it the case that every person in the relevant population was equally likely to be chosen for the sample? Or is the sample biased? Bias is a term of art in statistics. Right? For our purposes here, what it means is it the case that some kinds of people or some elements, some kinds of elements of the population are more or less likely to show up in the sample, right? So, sometimes you sort of, like particularly when there was, we just recently had the census, you had some worries about, well, if we don't do more to target particular groups, we're going to end up missing them, and if we miss them, sort of our data are not going to be informative about the overall population, right? That's a worry about bias. You know, our sampling methods, because we send mail to addresses, our sampling methods may be biased in the sense that they're less likely to capture homeless or transient people, right? That's a question of bias. If we ignore that, it's no longer going to be the case that what we learn from our sample will be informative about the population. Or maybe a better way to think about it is the population that our sample is informative about is a particular population, right? If our sampling methods cause us to miss homeless or transient people, we then couldn't, on the basis of the sample, make statements about what is true in the population in general. At best, we might be able to make statements about what is true of the non-transient, non-homeless population. Right? So you can think about it whichever way that you want. Right? Our sample allows us to learn about a particular population, right? But maybe not the population of interest. Okay? So that's going to be a sort of a first-order question. Hey, Miss Expert, hey, Mr. Expert, tell me about how this sample was collected, right? Is it likely that it was random? Or tell me about the sources of non-randomness, and how should that influence the way that I think about whether we can go from the sample to the population? Again, this is largely going to be a relevance inquiry, you know, a joiner type inquiry, okay? Sometimes the questions will be sort of simple, right? Well, hey, you know, Mr. Garza for the Vioxx case, imagine instead of 78 that he was really 71. And all the studies that we relied on had people from 50 to 70. You say to yourself, well, even though strictly speaking, the studies are only going to be informative about people in the age 50 to 70, really, come on, is 71 so much different? So I'm willing to sort of do the extrapolation there, right? How about 78? I might still be willing to do that extrapolation, but you can see it's a harder question, right? You can see that it's a harder jump, right? You're making more of a leap of faith there. If instead Mr. Garza was, 60 years old, he would have been smack dab in the middle of the sample study. And so you say, oh yes, I'm perfectly willing to make this inferential leap because as long as there are no other problems with the analysis, as long as there are no other sources of non-randomness, I'm willing to believe that those studies are informative about the population between 50 and 70. Mr. Garza's right in there, right? So sometimes these inquiries are sort of fairly simple. Either you're in or you're out. And I've got some mental model, or I've got some beliefs about the world. I think heart attacks get very different when you get much, much, much older. So I'm throwing it out, right? Well, no, I don't think heart attacks jump in crazy ways between 70 and 71, so I keep it in. But sometimes the questions become harder. So, take the case from the Daubert trilogy, the Joyner case, right? General Electric versus Joyner. If you remember the facts of that case, trial judge was presented with evidence. I forget what the substance was, but remember Mr. Joyner, he spent his work days sticking his hand in sort of lubricating goop for electrical transistors, and eventually he generated, he developed some cancer that had been associated in the scientific literature with exposure to exactly this lubricant. Trial judge listened to the plaintiffs. Plaintiffs provided research that was fantastic from an internal validity standpoint. This research involved exposing lab rats and chicks to the exact same substance. Had treatment and control, randomization, all the kind of stuff we're going to talk about in the next hour that sort of lead to a really good study. Trial judge says, this literature is sort of unassailable. I believe it from a reliability standpoint. I just don't think that results with respect to lab rats and lab chicks are very informative to results having to do with a human being. That jump is too large. That jump is too far for me to be willing to extrapolate, for me to be willing to generalize, right? A perfectly reasonable, a perfectly well-trained judge might just as well have said, nope, sounds good to me, right? There are tons of instances where we study lab rats and make the jump to humans, right? We study makeup on, or we used to study makeup on lab rats, and we do this all the time, so fine, I'm going to let it in. Joiner judge says, no, I'm not going to let it in. There is no statistician in the world who could arbitrate that debate, right? These are issues of judgment. Now, the statistician can sort of raise interesting issues. Statistician might say, well, let's think about how we studied the lab rats. You know, Mr. Joiner, 4 times a day for 15 years, was sticking his hands in for 3 minutes into this lubricating stuff. The lab rats, what did you do? Did you have them stick their hands in this stuff for 20 minutes a day, 3 times a day for 15 years? No, we took those sons of bitches and we stuffed them in a vat of this stuff and they swam around in it for 8 hours. Maybe that's a difference, right? Maybe that's a difference. And we can't know for sure statistically. I mean, there are ways that we could investigate it, but at least as a starting point, we have to use sort of our own kind of intuitions about the world, right? It's not strictly speaking a statistician's question. It's not even entirely a science question, right? That's why sort of we leave it up to the trial judge's judgment, I think, at least in my opinion, okay? How do we sort of make these determinations? So as a general matter, we might think about, well, are the dosages similar? That's the lab rat swimming in the vat versus sticking its little rat paws into the stuff. Dosages may be sort of important. Is the physiology between a rat and a human similar enough with respect to cancer, or this particular kind of cancer, that we're willing to make that jump, right? Interact those two things. Are the dosages and the physiology similar enough? How does the lubricating stuff actually lead to the cancer? Is it just sort of surface contact, right? If that's enough, okay, well then maybe the difference between swimming in it and sticking your hands in it is not so much. I mean, that's not so much of a difference. But maybe if it's ingestion, that makes a big difference, right? So there are questions that one could ask the scientific or the statistical expert, even if they can't answer the ultimate judgment, right? And that's all going to fall into this kind of relevance prong of Daubert, or this external validity prong of statistical inquiry, okay? Still no questions, so I presume it's working. So we'll keep going on, okay? To sort of tee up the next hour, since now we're down to sort of the last 15 minutes, to tee up the next hour, the main thing that we're going to jump to is we really want to sort of answer this causation question for virtually all policy and legal issues. Causation, although it's at the root of all of these applications, legal and policy applications, causation is as much of an art as a science. Most of what I've talked about so far is so much of just a science, just a, hey, write it down in the book, this is how we do it, that virtually everything I've talked about so far is completely automated in a sense. You give me the data, I plug it into the computer, it spits out, here's the mean, here's the median, here's the regression coefficient. Oh, you want to adjust for these other things, I'll plug them in too. Quite frankly, anyone can do it, right? My second-year law students who I do 3 weeks of regression and scientific evidence, at the end they probably can run regressions, right? It's mechanical, okay? Unfortunately, the big picture question about is a correlation, is a relationship causal, cannot be distilled down to just pure mechanical issues, right? Because, thinking back to the way I talked about it, How do you know that you've adjusted for enough stuff, right? Have you adjusted for enough? So let's take this relationship between education and income. I get a bunch of data on people. I've got data on 10,000 people. Let's assume it's a random sample. 10,000 is big enough, right? I've got data on their education. I've got data on their incomes. I run a correlation. It's a positive number. It's not 1. 1 would mean these things move in lockstep together. But it's positive and it's very high. So these things move together and they move fairly proportionately to each other. Okay? But immediately you say, well, but I'm concerned. What if it turns out that people who get more education on average, note all this stuff is pretty much on average. You can always find counterexamples. But I'm worried that what if people on average who get more education tend to be smarter? Right? Obviously there's counterexamples, right? Bill Gates, real smart, drops out of college. People who drop out of high school, quite smart. And we've all met educated fools, right? We've got Henry in the back. He's got 20 degrees. It's fun to have a beer with. You probably wouldn't let him make many decisions for you, right? There's always exceptions. But we're talking about on average. So you say, I'm worried. What if it turns out people who have education, a lot of education, also are smarter? And the reason I want to answer this question is for some policy reason. Should we invest in more education? Well, if it turns out that just being smarter, and note for the time being, I'm just assuming away the problems of how do we define how smart someone is. Imagine we solved that, right? Obviously we haven't. Obviously that's an area of controversy. But whatever you think is the metric of smartness, I'm worried. People who are better on that metric get higher educations. People who are better on that metric tend to make more money. That's all right. I can tell my computer, as long as we've got data on how smart the people are on whatever your preferred metric is, I put that into my regression. I adjust the correlation to reflect this. And it turns out that, hey, the relationship between education and income, it stays positive after I adjust for how smart you are, but it gets a little bit smaller. You say, aha, good, you addressed my concern. Now we can go forward with the particular policy. Then someone says, yeah, but I'm worried. What if it turns out independently of how smart someone is and independently of how much education they have, what I worry is that people who tend to get a lot of education have rich parents. And rich parents tend to have rich kids. And if I'm investing money in education, but really it's just kind of duplicating what rich parents are already doing, that's not really helping anything. You say, aha, I have data. I have data on how rich your parents were, so I put that into the regression, so now I've adjusted for it. Correlation between education and income stays positive, it now just got a little bit smaller still. We could do this all day, right? We can come up with intuitive stories that we think, oh, I'm worried about this, have you adjusted for this, et cetera, et cetera, et cetera. We can do this all day. Luckily, as long as we've got data on the thing that you're concerned about, we can make the adjustment. Regression, mechanically, can handle all of these adjustments. So we're in the clear, right? We can get to causation, right? As long as we've just adjusted for enough. Here's the problem. My little caveat was, as long as we've got the data. Now, in some things, conceptually, we can imagine getting the data. We just didn't happen to collect it. So the thing about how rich your parents are. We didn't ask you that when we were collecting the data. We could have, we just forgot. So we're screwed over for this particular study and this particular sample. But going forward, at least, we could answer that question by, now when we collect the data, we ask the question, how rich were your parents? Okay, so at least we have the way forward. However, there's going to be a bunch of stuff that we could never collect the data on. So what if it's the case that I'm worried that people who are more diligent tend to go to school more and tend to be kind of paid better? How do we quantify diligence? How do we quantify diligence? I give Bruce in the back, I give him a 10, I give Henry a 20, I give me a 10,000. Hey, I don't know what any of those numbers mean, right? And how do we know? How do we compare my diligence to your diligence? There are 5 million of these kinds of things you can think of: diligence, fastidiousness, conscientiousness, risk-taking propensity, etc., etc., etc. These things are fundamentally unquantifiable, and yet they matter in their relationship. So if we want to get from our regression or our correlation to causation, and we can't account for these unquantifiable, or sometimes economists refer to it as unobservable characteristics, then we're cooked. We're still not going to be able to make the causal claim. Okay? If there's one thing that you remember or think you remember from sort of high school or college statistics, it was correlation is not causation. Right? That's the thing everybody hears. Every undergraduate statistics professor says it. This is why correlation is not causation. Because there might be other factors, other variables that have not been included, and worse, could not be included, could not be accounted for, could not be adjusted for. Right? And with that possibility, you can never make a causal claim. Okay? Then you say, Jesus, Klick, what are we going to do for the next hour? Well, see, these guys, they ask me for a topic, I give it. They don't really know what I'm talking about, so you just make something up. Now, it turns out most of what we as economists do, and actually some other empirical social scientists do, is an attempt to get over this problem. And that's going to be what we sort of focus on in the second hour. But in my last sort of 7 minutes, 8 minutes here, I'm going to tell you how the science people get over it. Sort of, we social scientists, we're sort of the squishy soft scientists, but how do the lab coat scientists get over this issue? The way that they get over this issue for causality and these omitted variables is experiments. Okay? So the problem of the unobservable variable, the unquantifiable variable, is I worry that that unobservable variable might be related both to my outcome and to the thing that I'm trying to study. Right? So let's go back to Mr. Garza. Right? The legal question is, people taking Vioxx, are they more likely to have heart attacks? Right? If I just did a correlation out in the world, I would be worried. I would say, well, look, people who take Vioxx, they tend to be older, they tend to be fatter, they tend to be more sedentary, they tend to be X, Y, and Z, right? So I need to account for those things before I make a causal claim about a correlation. But then I raise, well, what about things that are hard to quantify, right? What if it turns out that there's a correlation between taking Vioxx and underlying stress levels, right? Can I really measure underlying stress levels? Yeah, maybe there are some proxies. Sometimes we use proxies for unquantifiable stuff that we think captures the thing that we're worried about. Note, in that situation, we kind of have to make the assumption that our proxy is a good measure of the thing that we care about, or the thing that we're kind of worried about. If we can't directly observe the main thing that we're worried about, how can we ever test whether the proxy is a good way to capture that? Right? We can't. We kind of have to assume it. So what if we're worried, hey, people who have higher stress levels are more likely to take Vioxx, and they're more likely to have heart attacks, and I can't get data on that? Here's where the science guys come in. Here's where Merck comes in. Here's where sort of the CDC and the FDA come in. they can run an experiment. How does an experiment work in this setting? Well, here's what we do. We get a bunch of people, all with the arthritis problem, let's say. We randomize, right? So we get 1,000 people, we flip a coin for each of them. If you come up heads, we're going to give you Vioxx or some COX-2 inhibitor, right? If it comes up tails, we're going to give you a placebo that looks just like the COX-2 inhibitor, but is really just, a sugar pill. And then we're going to follow, right? How does your arthritis get? That's the main reason we did it. We want to see, does this really work for helping arthritis? But then we also track, do you get heart attacks? So we can sort of see. Here's the thing, because we randomized between who got the treatment, the COX-2 inhibitor, and who didn't, i.e. the placebo people, flipping a coin doesn't care whether you're older, doesn't care whether you're fatter, doesn't care whether you have higher stress levels, doesn't care whether you're more conscientious, doesn't care about any of that stuff. That is, when you get the drug or not is entirely independent of any of those other characteristics. Therefore, those other characteristics can't be influencing the relationship between when you got the drug and your particular outcome. The science guys, the lab coat science guys, right? Bruce and I would claim we're science guys too, we just don't wear the lab coats. But the lab coat science guys, they use the experiment to get over this, right? Now you still have to ask questions. Was the experiment done right? Was there this randomization? Was it large enough, right? Those two things are going to be important. Was the sample representative of the population? Well, no, we picked particular people. Okay, so which population was it representative of? And is Mr. Garza, is he captured by that population? We still have all those kinds of questions, but at least for causality purposes, we've solved our problem, okay? So then why, if it's good enough for Merck and it's good enough for the FDA, why isn't it good enough for us policy types? Well, think about what an experiment would be for me. I'm interested in this education and income stuff, so I want to run an experiment. For the next year, every baby who's born in this state, we're going to flip a coin. If it comes up heads, they get to go get education. If it comes up tails, they don't get to go to school. You laugh. We can't run that experiment. We don't run that experiment. Many of the legal and policy issues that we're interested in, experiments are just not feasible. We'll talk more about that when we come back. I see two questions, so I'm going to lose my last 2 minutes for that. One is an important one that always comes up. I said for law of large numbers, the sample size has to be large enough, but I didn't specify for you. Every judge who I've ever said this to eventually says, okay, well, what's big enough? There are sort of two answers. The one answer is the answer that I give if I'm teaching my kids or if I'm teaching sort of undergraduate statistics. That answer is 30. 30 is big enough. It's a lie. It's a lie every one of us who has ever taught this class uses. Because quite frankly, for an undergraduate statistics student, they don't want to be there. I don't want to be there. They're never going to do this stuff ever in real life anyway, so who cares? They want an answer that they can write down on the test. I'm better off, they're better off. Unfortunately, this lie is so ingrained that it shows up in statistics textbooks. So you all will at some point in your lives have some expert come up to you and say, here, it says right here 30 is big enough. You got to accept my report. Here's the real answer. It depends, right? It depends. For some purposes, 20 might be enough. For some purposes, 20,000 may not be enough. How do you make that operationalizable for you guys? All other things equal, meaning I've got two studies, they look identical on every relevant dimension. One has a small sample size, one has a big sample size, or one has a smaller sample size, one has a bigger sample size. All other things equal, bigger is going to be more reliable. But all other things equal is an important caveat there. If you have a smaller sample size and some other stuff is bad, versus a bigger sample size where it's even worse, well, the bigger sample size might not be any better in that situation. I'm out of time, but let me take a look at the last question. To what extent are secondary or exploratory findings less reliable than primary findings? So somebody asking about data mining. We will bring that up in the second session. So let's go have our break. We'll see you in 20 minutes, I think.